Well, thanks everybody for joining us today. My name is John Simon. I'm the Product and Applications Manager for Ethernet products at Intrepid Control Systems. And I'm going to, over the next 45 minutes to an hour, I'm going to talk about the Ethernet switch and OSI Layer 2 in the context of how it is used in automotive networks. So after a brief intro, I'll talk about why we need switches. I made the comment on LinkedIn that at some point they're going to be in every corner of the car or every zone. So why is this and what do they do? Then I'll talk about the MAC frame, or also known as the Ethernet frame, followed by what the switch does with those frames. How does Ethernet work? Then we'll talk about VLANs. These are virtual LANs. And then I'll go into some detail about how the switch processes the Ethernet frames. And as well as talk about quality of service. This is the type of thing the switch does to manage priorities and make sure that latency and determinism are enforced on the network. And this is important for safety critical systems and autonomy, all of which are rapidly growing functions in the vehicle. I'll also briefly talk about time synchronization. This is also important with the autonomous systems, and then a brief summary. If you're not familiar with Intrepid Control Systems, we're a global company. We've been around about over 30 years. We supply network development tools for automotive. We're based in Troy, Michigan, where our headquarters is. All of our hardware and software and manufacturing are here, as well as we have offices in all the regions to support local sales and applications of our customers. So in Europe, in Asia, and South America, pretty much globally. So why do we need switches? Why are they starting to become more prominent in vehicle architectures? Well, when you look at networks in general, a network is a network, whether it's your house, whether it's your office. It's just a means of computing devices sharing information. And there are many aspects to networks that come into play when you want to choose a network for a given application or applications. So this chart here shows all the different trade-offs that are available and how different attributes of the system affect this. So physical layer has to do with the speed, with the media. Is it copper? Is it wireless? Is it optical? The topology is how the devices are connected. And then the protocols are all the different applications that run on the network for different purposes. So choosing these three attributes has a big impact on all these different aspects of the network. And after a long time, the CAN network in the vehicle was wasn't supporting all the services and all the bandwidth in the network. So trade-offs can allow you to optimize a network for a specific application, like CAN or MOST or FlexRay. So CAN was optimized for exchanging signals, information on vehicle speed, engine torque, door ajar, but it wasn't optimized for the needs of today. So trade-offs can also be balanced to meet the needs of multiple applications. And that's one of the reasons that automotive or Ethernet was chosen for automotive, is because of its versatility and its ability to adapt or meet the needs of new requirements. The different network topologies, it goes from anything from as simple as a point-to-point network, a bus, which has been historically the primary network, the CAN network in automotive, as well as LAN and FlexRay. There's a daisy chain topology for FireWire and a newer technology for audio called A to B. There's a ring topology, and then we have star and hierarchical star topologies, and these are the topologies of Ethernet, and fundamentally the switch is a primary part of the network as it connects all of the ECUs or computing devices together on a local area network. Switches eliminate collisions. So in traditional or legacy networks in the vehicle, some networks avoided collisions by scheduling. So LIN has a master and slave schedule. FlexRay has a rigid deterministic schedule. So when the devices all share the same media as they do in these two networks, the collisions are avoided by virtue of a schedule. CAN has something called non-destructive arbitration. So if two devices start to collide, there's a means for arbitration such that the node with the higher arbitration ID takes precedence over the lower arbitration ID. So there's no collision there, but there is arbitration. The unique things about Ethernet is, at least in 100 megabit, 1000 megabit, and multi-gigabit automotive Ethernet, is that they are point-to-point connections at the physical layer. And these point-to-point connections have full bandwidth in both directions. So there's no opportunity for collisions. These other media are all shared media. So they're sharing the bandwidth between all the devices on the network. For automotive Ethernet or Ethernet in general, a switch network is point-to-point connection, so there's no opportunity for collisions. So how does a switch work? Well, original Ethernet was actually a bus architecture like CAN. It had multiple nodes on a single media, and it managed collisions, as I mentioned before, with arbitration, which is inefficient, and the fact that the network shares bandwidth across all the devices. So most modern networks are switch network, connected by switches. And so each connection between the switch and the device is an independent network, full direction, full duplex, full bandwidth in both directions. And the switches route the traffic intelligently, buffer traffic to avoid congestion loss, and it's impossible for the frames to collide because, again, it's a point-to-point network between the two devices. Another reason you're going to be seeing more switches in vehicles is removing away from a domain architecture to what's called a zone architecture. So the existing and prior architectures called domains, all the domains were segregated by networks. And what I mean by domain is infotainment versus HVAC versus powertrain versus chassis. All of them had separate networks in the vehicle. And you can see this, as they call it, rat's nest of connections, a lot of redundant connections to different locations in the vehicle. So advances in technology in the last 10, 15 years have made it obsolete in terms of cost, in terms of weight, and complexity in manufacturing. So now you can see the zonal architectures is a very neat, very optimized power and signal distribution system, less weight, simpler assembly, more reliable, but there's a cost of this optimization, and the complexity and the other cost is to achieve this type of architecture. You need switches connecting all the devices around the zones of the car. So now we know why switches are emerging more in vehicles. Let's talk about OSI Layer 2, the data link layer, and how switches work. You can't go into a discussion of network or a specific layer of the network without at least explaining or introducing the OSI model. So OSI stands for Open Systems Interconnection. This was originally something that was created as part of a specific protocol suite. But over time, people realized that this model was really applicable to most, if not all, network technologies in one fashion or another. So it became kind of a universal model to describe different networks. So each one of these layers you can think of as where a technology or a service lies. So the physical layer being the media, so that tells you if it's electrical, wireless, optical, how the signals are encoded. Is it PWM? Is it Manchester encoding? The data link layer tells you where the lowest layer addressing is. So for Ethernet, it's a MAC address. For CAN, it's an arbitration ID. And as you move up the network, each layer is responsible to provide different services to network communication. So today we're going to talk about strictly the data link layer. We do have more broad courses on automotive Ethernet, anywhere from 2 hours to a full day, where we talk about a lot of these layers in more detail. So what makes this abstract model relevant? One thing is it aligns very well with our software development. We have layered software development. We have upper layers or applications passing information down to TCP and IP stacks. And so the OSI model is very good because it segregates the layers, the stacks from the application, and even the different protocols at the layers 4 on top of IP. It separates those as well. So data encapsulation, you have an application upper layer passing something to TCP. It gets a header, TCP header put on it. It gets passed down to IP. IP adds its header, and then it gets passed to the MAC layer, which is what we're going to talk about today, just before it gets converted into either electrical or optical or electromagnetic signals and transferred to the receiver. And then the receiver takes this packet and decapsulates it and passes it up the stack to the receiving application. The definition of the data link layer, it's also called the MAC layer. That stands for Media Access Control. And this is where on a network, the lowest level device addressing is defined, the formatting of the message, what's in the header, how big the payload can be, any sort of error detection or quality of service. And then the MAC frame or the Ethernet frame was designed to encapsulate higher layer protocols. So this, if you're coming from a CAN background, this would be analogous to the CAN controller. And this last point, LAN technologies generally span layers in 1 and 2. What that's meant is, for example, you use a MAC controller for Ethernet, you use an Ethernet PHY or physical layer for Ethernet. You use a CAN controller for CAN, you use a CAN transceiver for CAN. You wouldn't use a CAN transceiver with a MAC controller or vice versa. Usually the physical layer is very tightly coupled with the layer 2 of a given technology. This is the Ethernet frame. This is the lowest level data structure that carries all data on Ethernet. If there's a packet being transmitted on Ethernet, it has this structure. It's sometimes referred to as the MAC frame, and it specified the needs of OSI Layer 2, which I just described on the previous. It addresses device addressing, message formatting, error detection, some quality of service aspects, and it can carry between 46 and 1,500 bytes of data. The addressing, or the MAC address, it's a low-level physical network address. It's usually programmed or burned in fuses into hardware devices. It's 6 bytes long. It's usually globally unique, and I'll explain why I say usually in a second. The first 3 bytes are what's called an OUI, organizationally unique identifier. So this is like a signature for a given company. A company makes Ethernet devices. It pays a registry to reserve a block of addresses, and then they use that on all their products. The last 3 bytes are unique to the device, almost like a serial number. So this address is used to direct data on all Ethernet networks. So it could be Wi-Fi, it could be optical, it could be copper. It's the source and destination addresses are in the first pieces of information in the MAC header. And certain bit patterns imply the type of addressing that's being used. And what I mean by that, so you can have unicast addresses, multicast addresses, and broadcast addresses. So
John,
yes.
Sorry to interrupt. There's one question about would the encapsulation include cryptography as part of the cybersecurity strategy?
The encapsulation,
Yep.
so the encapsulation, yes. If you were using well, it depends. There's security at layer 2. It's called MACsec. And so it's security that's limited to this. Yeah, sorry, jumping around here. Data link layer. There are different security measures for different OSI layers. So there's MACsec here. It's IP, you have IPsec. At layer 4, you have TLS, transport layer security. In layer 2, there is encapsulation for encryption and authentication in the form of MACsec.
Thank you.
So unicast address is point to point. It's used to send to a specific node, like a client server type of application. There's something called a universally administered address, or UAA. And this means that the MAC address is globally unique. There are no two devices on the planet in the universe that have the same MAC address. And that's because if there are MAC address conflicts, Ethernet doesn't work. There's just no way around it. Every device on the local area network or the network needs to be unique. So these are usually assigned by manufacturer when the device is produced. And the way you identify a universally administered address is the first least significant bit of the first octet of the MAC address is 0. And I say octet, this is a term that is used by IEEE for byte because historically, believe it or not, a byte was not necessarily 8 bits. They had a 4-bit byte, and they talked about. So octet took all the ambiguity out for the purposes of writing the IEEE specs. Now today we know a byte's 8 bits, and that's the end of the story. But in the early days, that was not the case. Moving on. So the first octet, or the first byte, if the second least significant bit is a 0, you know that there is no other device on the planet, or there should not be, that has a conflicting address. There's also something called locally administered addresses. And if the least significant bit is a 1 here, that tells you that it's not necessarily unique. And it's probably something that was designed to be on an engineered network or an automotive network. And that's where it's not a public network. You can't just plug anything on it. You design the devices, you pre-assign all the MAC addresses to make sure they don't conflict. And in the cases of automotive, it's not going to be uncommon that every instrument cluster is going to have the same MAC address on a given vehicle platform, or all the radios will have the same MAC address. And that's okay in an engineered network because it's not a public network. You shouldn't be plugging just any device in there. All the devices need to have pre-selected non-conflicting MAC addresses. You have multicast addresses, or one-to-many. And this is something that's used for protocols like discovery protocols, where a device advertises, hey, who's out there? What are your services? Who can I talk to? Those types of protocols. And if the least significant bit of the first byte is a 1, that tells you that it is a broadcast message. So if you see a 0-1, that's one of the more common first bytes that you'll see on a multicast address. And then there's broadcast, which is the special case of a multicast, and that's where all the bits of the destination address are 1. The intent of that is to go to every device on the local area network. The MAC header information. So after the source and destination addresses in the header, there's something that originally was just to find the length of the Ethernet frame. As Ethernet evolved, they realized that that was very short-sighted. It wasn't going to make Ethernet very extensible. So they repurposed this field in the MAC header to be something called an ether type. So for backwards compatibility, if there's a value here less than 1536, the maximum size of a Ethernet frame with all the header information, that tells you that it's the old type of Ethernet frame, and this is just the length of the frame. Values greater than this are IEEE assigned values, and this is a table of the more relevant ones for automotive. So as I said, anything less than 0600 is a legacy frame. And then it's a matter of parsing through this table to tell you what information is in the remainder of the Ethernet frame. So we'll talk about VLAN tags in a second, but if you see these values, that tells you that there's a VLAN tag, or there's a redundancy tag. This is for reliability. There's a protocol that allows duplicate frames to be sent and across the network, and then the receiver throws the redundant frame away. MACsec, I mentioned earlier, has a special ether type, and that tells you that there's security information and the frame may be encrypted and it's probably authenticated. Then you have IPv4, IPv6, ARP. These are all widely used outside of automotive. And then these AVD and TSN ether types, 1722s for streaming media or streaming encapsulated networks. And then GPTP is a precision time protocol. So all of these indicate the type of information that's going to be encapsulated in the frame following the MAC header. So we talk about a MAC frame. So what does a switch do with this? Well, fundamentally, a switch connects all devices on layer 2 and provides all the services and support on layer 2 for the MAC layer. So addressing, quality of service functions. It conserves bandwidth by intelligently forwarding the frames based on the MAC address. So it's not broadcast across the network. The switch learns where the information needs to go and sends it only to that location. And the importance of this is the bandwidth bandwidth conservation between devices. So we have a switch here, and I have a media or head unit connected to an amplifier through the switch, and then I have two video devices connected with a separate stream. These are independent streams going through the switch. So each port is an independent physical connection. There's no opportunity for collisions. And consequently, each one of these has 200 megabits of bandwidth per connection, 100 megabits each direction. And the switch intelligently forwards it only between port 1 and 3 for this stream, and only between port 2 and 0 for this stream, to effectively get an aggregate bandwidth of 400 megabits between these devices, despite the link speed only being 100 megabits per direction. It also does quality of service things. It throws away bad frames. We'll talk about VLAN enforcement. This is a kind of like a traffic cop type of service. It prioritizes traffic. It can limit the rate of traffic, and there's other protocols to manage latency and determinism. How does this intelligent frame forwarding work? The switch has something in it called an address translation unit, and it's a simple table that tells the switches where to forward the frames based on MAC addresses. So the information stored in this table are the MAC addresses, and then the destination port vector. The destination port vector is a bitmap of which port the MAC address should be sent to. So if you were to look at, let's look at this second line here, bit 0 is a 1. So that tells me that the switch knows anything with this MAC address is going to go out port 0 and only port 0. If we go down 2 rows, you'll see this port vector has multiple destinations. So it should be no surprise that the first byte is a 0, 1. That tells you that it's a multicast address. So when this destination address arrives in a switch, it'll be sent out all of these ports. There's also VLAN information and priority information here as well, and we'll talk about that shortly. There's different ways to configure how this table works. The first one's a dynamic table. This is most common that you're probably familiar with. It's a plug and play. You buy a switch at Best Buy or Micro Center, you plug it in and it just works. And the way this just works is the switch has, when it boots up, it has no knowledge of what is connected to it. So this table here is empty. And as it receives messages, it doesn't know where to send it. So it floods it or broadcasts it out all of the ports with the expectation if that address is out there, it's going to respond. And the minute it responds, it can make an association with the message it received in response and which port it's on. So the switch builds this table by inspecting all of the frames it receives. There's also a static table, and this is where you would pre-program this table, and you could even lock it down to the point where if addresses are not in the table, it can throw them away, or you can have it flood all the ports, which is similar to this dynamic table. So the dynamic table, again, plug and play, it's unlocked. Some would consider that a security attack surface. So in automotive, I think the most prominent strategy is to have a static table where everything's pre-programmed. There's no attack surface there. And there's no reason that you can't, because again, I use this term engineered network a lot, but an engineered network like automotive network, you know all of the MAC addresses up front, so there's no reason you couldn't pre-program this. VLANs or virtual LANs. This is a quality of service mechanism at layer 2 used to optimize bandwidth and also has some security implications. And this is where the switch is a traffic cop and it enforces rules based on memberships of a virtual LAN. So in this switch, we have virtual LAN ID 1 and we have virtual ID LAN 2. And what this means is the switch is programmed such that anything coming in on ports 1, 2, and 3 can under no circumstances go to any of these ports 4, 5, 6, 7, or 8. Conversely, anything with it's programmed to be VLAN 2 cannot egress to these devices. And there's two ways that switches can implement this. One's called port-based VLAN, and the other one's called VLAN tags, and that's the additional information in the MAC header. Port-based VLAN is pretty simple to explain. The paths of between ingress and egress ports, so ingress being the ports with the data coming in and egress exiting, the path between these two are explicitly enabled or disabled. So in this table here, I have all the paths between port 1 and port 2 enabled, and port 1 cannot egress out port 3, 4, 5, 6, 7, 8, or not, or any of these ports, but it's enabled between port 1 and 2. So this is an exclusive connection between these two ports, and all of the remaining ports are disconnected. Conversely, if you were to fill out this table this way, you would have a second VLAN ID in this group. So anything on port 1 and 2 can exchange communication freely, but not to these ports and vice versa. VLAN tagging. So port-based VLAN, there's two shortcomings. One, it's a static table. It's typically not something that's changed during runtime. The other is it's all or nothing, meaning anything that comes into that port falls under those restrictions of the VLAN. So there's a lot of different information on the network, and it needs to be, it's helpful if it can be treated differently. So VLAN tagging is optional content in the frame that helps switches isolate networks, control bandwidth. And so a VLAN ID defines where the frame can and can't go based on rules in the switches. The VLAN tag also contains something called a priority code point, and that tells the switch what types of quality of service guarantees should the switch offer to this type of the traffic. And then if you see 8100 or 9100 after the MAC address information, that tells you that there is a VLAN tag in the frame. So what is this and these VLAN tags, if you're using Windows and you're looking at Wireshark or using Vehicle Spy or Software Vehicle Spy, you may or may not see the VLAN tag in the traffic. In the case of Windows, by default, most of the network drivers strip it before it's passed up to the applications that you're using to view it. In the case of Linux, for whatever reason, I don't think I've ever sat down in a Linux console and not seen VLAN tags. So if you need to see these in Windows and you think they should be there and they're not, you'll maybe need to dig around and find if there's a way to enable this in the network adapter driver. The information in the VLAN tag, the first is a VLAN ID. So that's just a unique identifier between VLANs. So VLAN 1, 2, or 3, each one's an independent VLAN. It's a 12-bit value. So that means you can have values between 0 and 4095. There's a drop eligible indicator. So this is a quality of service flag that switches can use to if a given stream is only supposed to have a certain amount of bandwidth and the switch identifies that it's exceeding that bandwidth, it can set this indicator and that will tell their devices that this frame is violated its quality of service guarantee and it can be dropped if necessary. And then this priority code point is a number from 0 to 7, and that indicates the priority of the frame relative to other frames. Sometimes you'll hear the term VLAN, and you'll hear like VLAN 2 or VLAN 3, and what that is meant to imply is VLAN ID 2 or VLAN ID 3. VLAN and VID are used interchangeably. VLAN is all of this information together, where the VLAN ID is one piece of this information. But if you hear VLAN 2, they're most likely talking about VLAN ID 2 or VID 2. Now let's talk about how the frame or how the switch forwards all these frames. So this is a picture taken out of 802.1q. That's the IEEE 2000 page light reading that defines how switches and LANs work. I've kind of changed it, made it a little more friendly for presentation purposes, but each one of these is the same stage from the 802.1q document. So the first stage of a switch is it ingresses the switch. The switch eliminates frames with errors if they're oversized, if they're undersized. And an important thing to understand about a switch is that it's a store and forward device. It needs to receive the entire message before it starts sending out another port. And this is required for quality of service. It needs to receive the last frame of the Ethernet, the MAC frame, which is the checksum, to evaluate whether the messages are corrupt. If it's corrupt, then it throws it away. Again, that's a form of quality of service so that you're not sending garbage across the network and consuming bandwidth. There are cut-through devices that it's almost like a first in, first out type of transmission. So that can be a configuration on some switches, but then you're giving up the quality of service of it throwing away bad frames. The next stage, there's two stages that are more or less the same. This is where VLAN IDs are evaluated and compared against the ingress or egress filters. So if a frame comes in with a VLAN ID of 2 and that the frame or the port that it's coming in on is not a member of that port, it gets thrown away. If a frame is egressing the switch with a VLAN ID of 3 and that port is not a member of VLAN 3, then it gets thrown away as well. Frame filtering, this is where the switch determines what port it needs to egress, but it also enforces different switch policies. So you can have rules in the switch that tell it to throw away unknown VLAN tags, frames without VLAN tags, frames with VLAN tags. This is where you would configure it to drop all unknown destination addresses. And there's also reserved destination addresses for special protocols. For example, like GPTP has a special destination address that's used, and that's usually forwarded to a host processor in the switch as opposed to being forwarded out of one of the ports. Next in the pipeline would be flow metering, and this is something based on a token bucket algorithm. It's called MEF 10.3, and the switch has the resources or capability to restrict the average flow of traffic or committed information rate in terms of bits per second. Doesn't need to be a strict metering. It can be configured to allow bursts of traffic of certain sizes. And it can also be selectively applied to certain classes of traffic based on their VLAN or MAC address. So it doesn't have to be all the traffic coming in or one port or egressing a port. It can be selectively applied to different classes of traffic. The way the token bucket works is the cost of sending one bit, think of that as one token, and you have a bucket, and the bucket is being filled by these tokens at the committed information rate, or the flow rate that is the maximum rate. And the tokens accumulate in this bucket until the bucket's full. When the bucket's full, this is the committed burst size, or CBS. And the bucket stops accumulating tokens when it's full. When a frame arrives, and a frame is being queued to egress, the size of that frame is compared to the number of tokens in the bucket. If there are equal or more tokens in the bucket, the frame is colored green and allowed to egress. And then the bits or the tokens are removed from the bucket. If another frame arrives, and it's in this case 512 bytes, there aren't enough bits or tokens in the bucket, so it's colored red and thrown away. There's also variations on this. There's something called a dual token bucket, or a 3-color instead of red and green, it's red, yellow, green. So there's an excess token bucket. So very similar to, there's an excess information rate, there's an excess burst size. And so when frames are egressing, they look at the committed token bucket. If there's not enough tokens, then it looks at the excess token bucket, and then decides whether the frame should be sent or not. And then there's a lot of variations on how these buckets can be configured. You can have tokens overflow from one to the other as well. After flow metering, we have frame queuing. So each port of the switch contains 8 egress priority queues. And this is where that priority code point is used in the VLAN tag. The PCP tells the switch which queue to put the frame in. So there's 8 queues. There's up to 8 different unique traffic classes. So in more advanced functions of the switch, each queue has more than just a priority. You can have traffic shaping, you can have gating. And so what I mean here is each queue can offer or impose different qualities of service based on of traffic based on which queue it's placed in. Once the queues are full or being filled, there's many quality of services that dictate how the queues are emptied. The simplest is strict priority. Queues are emptied in order priority. If a higher priority has contents in it, the lower priority queues are blocked until the higher priority is empty. This is the simplest and easiest to explain, but it's also the most problematic because it leads to congestion loss. And this is where low priority queues are blocked by bursts of high priority traffic, and consequently, the switch doesn't have infinite memory, the queues overflow, and frames are dropped. There are things called enhanced transmission selection. This is kind of a generic term for different algorithms to avoid network congestion in emptying the queues. Probably the most known one is something called weighted round robin. So that means each queue gets a time slot to empty its contents. Those time slots are weighted so that higher priority queues have more time than lower priority queues. And then there's even more complicated algorithms in AVB and audio video bridging and time sensitive networking. And these are all aimed at eliminating the congestion loss I mentioned, but also bounding latency, making sure latency is under control, and imposing or delivering some sort of determinism onto the network. One function that a switch can do as part of in development or diagnostics is port mirroring. This can be used for monitoring. It does have some drawbacks. So you can configure a switch to, in this case, anything on port 1, or sorry, anything ingressing on port 2, 3, and 4 can be forwarded to port 1. So you can look at the aggregate traffic of all of these devices connected. The downside of using a switch in this way is bad frames aren't forwarded typically because switches are by default throw away bad CRCs or bad checksums. If you have a managed switch, some of them can be programmed to pass bad frames. There's also timestamp limitations. The switch doesn't have any timestamp capability. All the timestamps are done in your operating system of whatever computer you're using. The timestamps are also not when they arrived at the switch. They're when they arrived at the computer. And so consequently, the frames may or will likely arrive in the computer in out of order of how they arrived at the switch. Partly because of how switch queuing works, but also because of the store and forward aspect of the switch. If the device on port 2 sends a very, very large, a large frame, and the device on port 3 sends a bunch of, let's say, dozens of small frames, all the small frames are going to arrive here before the large frame. So they'll be out of order. You also can't strategically indirect traffic. If all these devices have, if you want to send a message specifically to one of these devices, the switch is going to send it where it thinks it should send it based on the rules in its configuration, not necessarily on what your application in the computer wants to do it. There is a means around this if you need to monitor traffic, and some of these limitations are problematic. There's something called an active tap. It's basically a man-in-the-middle type device where you have an FPGA or some sort of device like that that makes copies of the frames, timestamps them precisely, and sends them to the computer. I talked about quality service in general. I'll talk about a little more in depth or exactly what I mean by quality service. So it's a measure of how the network's ability to support multiple applications and all their requirements or needs. So now in a vehicle, you have infotainment sharing network resources with autonomous functions and with braking and with all the vehicles and networks. So quality of service means that we need to make sure that the traffic associated with safety critical is treated with a higher priority, with bounded latency, with determinism. So different applications have different types of traffic requirements. So these are all guarantees in terms of bounded end-to-end latency, determinism, and then high availability or reliability. Traffic classes infer that specific quality of service guarantees are applied to a traffic class. And you'll probably hear the term best effort. And best effort traffic is in reference to network traffic that has no quality of service guarantees. So how does a switch differentiate between these different traffic classes? It's got some resources in it called TCAM, or ternary content addressable memory. It's the technology, if you've heard of deep packet inspection, that's the underlying technology. And so there's a bit mask typically that you can define in the switch. And that bit mask, you would have it look for a specific MAC address, a specific VLAN. In some cases, you can go all the way out into like the layer 3 or 4 head, so you could set masks on IP addresses or ports. When that mask matches or a hit occurs, that tells the switch that that frame is part of a rules triggered, and that frame is treated with the quality of service guarantees associated with the traffic class. Traffic conditioning is a general term for manipulating how the Ethernet frames are sent to manipulate the behavior of the network. So this can be in terms of avoiding congestion or improving determinism or managing latency. So there's traffic shaping. So frames are buffered to allow unique scheduling and to achieve a specific quality of service goal. So this could be, in a lot of cases, this is trying to minimize bursts of traffic where high priority traffic might cause congestion loss. So if there's a huge burst, the switch will do something to intersperse the lower priority traffic. And then there's traffic policing, and this is along the lines of the token bucket. There's other algorithms that are associated with traffic policing, where it manages the stream not exceeding a designated bandwidth or frames per second. In network design for audio video bridging and time sensitive networkings, one of the main mechanisms to ensure that you get acceptable performance on the network is a stream reservation, and then the stream reservation applying traffic conditioning to the streams that are reserved. So usually the rule of thumb is when you're designing a network, only reserve 75% of the bandwidth for time sensitive streams or high priority streams, and always leave 25% network bandwidth for best effort traffic. And managing the multicast and paths and VLANs is only part of the solution. So the specialized switches, they manipulate the delivery Ethernet frames by a variety of methods. There's traffic filtering, traffic metering, and then there's traffic shaping. So this credit-based shaping is what I was talking about, where it ensures that the high priority traffic has sufficient bandwidth, but it also ensures that if there are bursts of traffic, that it doesn't completely choke out or stop the best effort traffic and avoids congestion loss. There's also time-aware shaping that's along the lines of there's a period of or a cycle time, and every beginning of that cycle time, high priority traffic is transmitted. It has a time slot every period to transmit high priority traffic. You can combine these. It's not recommended. A lot of these shapings or traffic conditionings work well alone, but when you try and combine them, they have interactions that make things actually worse. There's per stream filtering and policing. So this is if the traffic metering would be limited if it couldn't apply to selective traffic. So there's stream filters, uses the TCAM technology to identify information in the header, whether it's the VLAN or the MAC addresses, and it specifies which stream which gates and which rate limiters apply to the stream. There's also, you can have time gates. So these streams or these filters can be turned off on a schedule. So in this case, at a very high level example, you have talker A, it's transmitting through a stream gate, 20 megabits. There's no problem there. Talker B here is transmitting 90 megabits per second, but the network design was only for 20 megabits per second. So the switch can rate limit this to 20 megabits per second. And then also security threats. So if there were streams that weren't identified or there's information it didn't match the VLANs and the MAC addresses expected by the switch switch can block the traffic as well. Seamless redundancy. This has to do with reliability and availability. There's a protocol called frame replication and elimination. So the switch has the ability to create duplicate frames of a stream and send it 2 different paths across the network to another listener or another switch. And so if one of these paths has a problem, if the switch goes down, if a link goes down, the information still arrives. The header information has basically a serial number, so the receiving device knows which frames to throw away, the redundant frames. This is a form of redundancy. It's being looked at by some of the OEMs. It's not something that you want to do for high bandwidth because you're basically designing in the need for twice the bandwidth. So they're using it very judiciously, but it's something that's being considered. Lastly, we'll talk about generalized precision time protocol. This is something that the switch has a primary role. An example when you need this is sensor fusion. So if you have cameras and sensors around the vehicle and data is being collected from all corners of the vehicle and it's passing through different ECUs and being collected by a central control unit. The problem is the timestamps of all these pieces of information need to be synchronized. Otherwise, when they arrive at the central ECU, they're not very useful. So the camera timestamps, these wheel sensor timestamps, something needs to synchronize all the devices in the vehicle so that the timestamps are consistent. Generalized Precision Time Protocol, or GPTP, is defined in this IEEE spec 802.1as. It's called generalized because it's a reduced scope of IEEE 1588, which is Precision Time Protocol. 1588 is a standard that covers everything, all the time synchronization on Ethernet. So it's used for factories, it's used for professional audio, for like audio in stadiums for concerts and things like that. So generalized is a reduced scope to make it simpler and more cost effective to deploy in an automotive network. So the goal is 500 nanoseconds accuracy over 7 hops. So hopping across 7 switches, the devices their time should be within 500 nanoseconds of each other. And the way it works is there's a grandmaster. That grandmaster is connected to the local area network, and all the devices on the network synchronize their clocks to the grandmaster. It takes more time than I have here to explain how this works, but there's 2 primary responsibilities or how this works. One is the GPTP helps measure the time it takes the message to go from the one port to the other. So how fast the electrons take to come out of this port and into this port. And then it also measures the amount of time it takes for the frame to ingress one port and egress a switch. So this endpoint here, GPTP measures this time, and this time, the time it takes to hop between each devices. It measures the time it takes to go through this switch, the time it takes to go through this switch, and then it has all the latency information it needs to calculate its offset from the grandmaster clock and be synchronized with the grandmaster clock. So in summary, every frame of data on Ethernet is wrapped in a MAC frame. Switches connect the devices to a LAN and use the MAC frame, the information in the MAC frame, the VLAN information, the destination source address information to forward frames intelligently, to conserve bandwidth, to impose or deliver quality service guarantees. So bandwidth's optimized by the L2 address table. And switches have been evolving and constantly evolve, specifically for services required by video bridging and time-sensitive networking. So for streaming audio data, for time-sensitive networking, for safety-critical systems, VLANs, the priority queues, traffic shaping, rate limiting, managing redundancy, time synchronization. These are all functions that the switch or services the switch delivers to make a network work for all applications, sharing the resources of the network, sharing the bandwidth, sharing the switch connections. If you're curious what automotive Ethernet switches look like, at least in development tool standpoint, we have a few products. If you're interested, you can contact us for a demo. But basically, this is one example of a switch. It's got 500 base T1 ports on it. It has 2 gigabit ports with some options to change the physical layer, whether it's automotive Ethernet or regular Ethernet. It's got an embedded processor with CAN and LIN. We also have a larger switch with higher speed ports. It has 6 gigabit ports, 2 10 gig ports, a USB Ethernet bridge. It's got some resources in it to support embedded Linux development, and then also CAN and LIN. So these are the types of network development tools with switches that are available. If you're curious about how they work or want more detail on them, by all means, please contact us. Here's the contact information for our sales and technical support. My email address is down here in the bottom. And Arpin, were there any other questions that popped up along the way here?
Yes, we have one more question.
Okay.
Nikunj asked if we connect MACsec automotive Ethernet to without MACsec switch for just pass-through, is it work for just pass-through though?
Well, automotive MACsec that's being defined in Open Alliance TC17 is only MACsec point-to-point or hop-to-hop. So that would be out of scope for automotive because the MACsec only works point-to-point. If the question is, would the switch pass it? Probably. It definitely could. It would depend on how the switch was configured, but to the switch, it's going to see, it will see MAC addresses. So it will be able to look at the address table and if there's an address there, intelligently forward it. But in practice or in application, that wouldn't be the case in a car because the MACsec is a point-to-point type of service.
Thank you.
Okay, well, thanks for everybody for joining. And this is a very small section of a much larger curriculum that we have. If there's more interest, we can tailor this to 2 hours, 4 hours, a whole day. We've done workshops on different applications in time-sensitive networking or switches. So if you have a critical mass, this type of stuff and training is one of the more enjoyable parts of my job. So please contact us. I'd be interested to see what you would like to learn and if we can help you. And I think that wraps it up. So Yeah, I look forward to hearing it from everybody. I hope everybody found this helpful.
Thank you. Thank you everyone for joining.